homogeneous second-order linear differential equations with constant coefficients. These equations can be written in this form. There's a standard approach to solving them. It starts by assuming this solution can be of the form y equals a to lambda x, which means when we substitute it into this equation, we get a nasty looking equation. We get lambda and lambda squared from differentiating y once or twice. But since e to lambda x can't be 0 and we're taking a not to be 0, we end up with a quadratic equation known as the auxiliary equation. Now, depending upon the value of the discriminant for this quadratic equation, we might have two real roots, one repeated real root, or two complex roots. And these lead to three different possible sorts of solution to the differential equation. So let's consider the first case, where the discriminant is positive, the two roots are both real, so we can write y is a e to the lambda 1x plus b e to the lambda 2x, where lambda 1 and lambda 2 are the two solutions to the equation. So we get some sort of exponential, possibly even hyperbolic behavior, and depending upon the values of lambda 1 and lambda 2, it's exponential growth or exponential decay. So here's an example. If we're asked to find the general solution to this equation, what is it we do? We just put it into the quadratic equation, factorize it, solve it, and so we get our general solution. Okay, the general solution, of course, is where a and b haven't yet been worked out. Because it's a second order differential equation, there are two constants of integration, and we will need two boundary conditions or initial conditions to work out the values of a and b. Let's move on to the second case. When the discriminant is 0, we have two solutions, one of which is exponential and one of which is x times that exponential. Why is that? Well, because we have a repeated root to our, then if we didn't multiply by x, we'd have two terms exactly the same. And a standard approach is if you're going to get a repeated function, you multiply by x. Okay, so in this case, we're trying to now solve a problem with a boundary condition. And so what we do is we work out the auxiliary equation and we solve it. And remember, in this case, we get lambda equals 3 as a repeated root. So we take the form of y to be a e to the 3x plus bx e to the 3x. Okay, then we're going to put in our boundary conditions. We'll start with a simple one, y equals 1, x equals 0. Okay, the b term disappears, therefore we get a equal to 1. Then we differentiate our provisional solution. We put x equals 0 into that. We get b to be minus 3. So our final solution is e to the 3x minus 3x e to the 3x. That satisfies the differential equation and also the boundary conditions. Sometimes people ask, why is it that multiplying by x works? Well, one of the best things you can do is substitute it back into the differential equation. So we could take this, our general solution in this case, y equals a e to the 3x plus bx e to the 3x, differentiate it once, we've done so already, and differentiate it a second time, and we would indeed be able to confirm that x e to the 3x does satisfy this differential equation as well. You might like to try that as an exercise. The third sort of solution is where the discriminant is negative and we get complex roots. And because they're complex, yes, we could write them as e to the, in brackets, alpha plus I beta x, and a similar one for alpha minus I beta. But we can actually use Euler's relationship to change e to the I beta terms into cos beta x and sine beta x. And this is always much easier to deal with when we're trying to solve the problems. Okay, so here's now an example where we do this. We're going to find the solution to this equation here. Okay, and it's set up so that, and with this boundary condition. So first of all, let's solve find the general solution. We get our quadratic equation, we complete the square to solve it, and we get our values of lambda. And so we now know what our general solution is going to be like, because the real part is -1, you've got an e to the minus x, a cos 2x and b sine 2x. Let's just have a think about that solution. The sines and coses means it's oscillating. The e to the minus x means it's going to be decaying with time. So actually, this is a problem of damped simple harmonic motion. Okay, but we've got to now find the particular solution for these boundary conditions. So we've got this as our general solution. When we take the first boundary condition, x equals 0, y equals 0, that very quickly gives us a equals 0. For our second boundary condition, though, we need to differentiate, which is getting a bit more awkward. We get 4 terms, but we already know that a is 0, and we're also putting x equals 0 in, which means the 2 sine terms disappear. So we get our dy by dx being 1 is equal to 2b, so b is a half, and so we can get our final particular solution. Okay, still we can see it's decaying oscillating motion, it's damped simple harmonic motion, and if you haven't realized, these things damp quite quickly. Okay, by the time you've gone through one cycle and x here reaches the value of pi, you've got e to the minus x is e to the minus pi. That's about 1/20th, so it's already very small after one cycle. So that's how we solve these homogeneity equations, but more generally we have to solve problems where there is a right-hand side to our differential equation, which might be seen as being a driving force, for instance. And in this case, we've also got to find the particular integrals to add on to our general solutions. And that will be the subject of my next video. Thank you very much for watching.